Hello students, welcome to your second lecture. In keeping with what we discussed during our first class together, all of your lectures will be posted online. Today's topic is soil classification. To review, during our first meeting together, we did some housekeeping during which I outlined the course and indicated to you how it would be delivered to you. Practice quizzes were uploaded for you to use to personally gauge how much you need to review the topics you covered during CON 8411 and CON 8412, that is the Construction Materials 1 and 2 courses. Also, all dates for lectures, assignments, labs, and tests are now available for you on Blackboard and under the CSI, the Course Information document. With the present lecture, we will cover some new-ish material pertaining to soil classification. This will be important because, well, it's an important topic, but also because it has to do with your first example of laboratory work, Assignment 1. Out of curiosity, do you know when Assignment 1 is taking place and when it's due? If you don't, it is really important that you check out the Assignment 1 folder on Blackboard under Assignments and Labs, and also have a look at your CSI document. What we commonly refer to as soil is actually the byproduct of rock undergoing weathering. For the purpose of review, let's list the different types of rocks, soils, and weathering. Please note that, since this is a review, I will not cover this in great detail. Rather, I expect you to review these topics if they are a bit fuzzy on your own. There are three different types of rocks: igneous, sedimentary, and metamorphic. More info is found on the appropriate page of your textbook, where you can see more information about the difference between these three types of rocks. Soils are typically divided into coarse-grained and fine-grained based on the size of the soil particle. More on this later in the lecture. Finally, the weathering process, which causes rocks to become soil, may either be mechanical or chemical. A bit more info about this can be found in your textbook. I expect that you're probably familiar with using the term coarse-grained and fine-grained soil as part of the everyday lexicon. In general terms, coarse-grained soil is made up of particles which are larger than 0.074 millimeters, or a 200 sieve, just like the gravel in this photo. Whereas fine-grained soil is made up of particles which are smaller than 0.074 millimeters, just like the sand in this photo. When it comes to properly defining soil particles, simply differentiating between coarse and fine-grained soil is not sufficient. As we will practice during our Assignment 1, it is necessary to be able to know with much more detail the distribution of various particle sizes within any soil sample. But how is this done? More importantly, why is this done? As it turns out, if we know a soil's composition, we know its strength. And if we know a soil's strength, we know what it can support. And I mean what kind of load it can support. For example, based on this picture, do you think the soil under this road was strong enough to support the traffic above it? What about this picture? If you're thinking that perhaps the soil under these roads was not adequate to support vehicular traffic, you're correct. So why were these roads built over this kind of soil? If you're curious to know the answer, please ask me in class, and I will let you know. Anyway, this is why it's critical that, just like with any cooking recipe, we must know exactly the quantity of each particle size comprising a soil sample to ensure we know that soil's property, and therefore its strength. This is exactly what we will be doing for our first assignment, assignment number 1. Each of your groups will be given a soil sample, which you then will have to sift through increasingly smaller sieves, like the ones displayed here. You'll have to make proper note of the percentage of the soil sample which is retained in each of the sieves, so that you may be able to identify the sample. The results from your lab will then be plotted on a logarithmic graph like this one, so that you may be able to graphically view the distribution of different grain sizes with your sample. Let's review some of the coefficients that will assist us with identifying a soil sample after we've completed the lab. Let's start with the coefficient of uniformity, Cu, which is a measure of how uniform the soil sample is, or, in other words, are most particles the same size? The formula for the coefficient of uniformity is D60 divided by D10, where D60 represents the largest particle size you can read off your log chart that is smaller than 60% of the sample material, whereas D10 represents the largest particle size you can read off your log chart that is smaller than 10% of the sample material. Confused? Don't worry, we'll work on an example together. The next coefficient is the coefficient of curvature, Cc, which is a measure of how smooth the curve is that you plotted on the log chart, or, in other words, is the curve smooth and free of unexpected dips and peaks. The formula for the coefficient of curvature is D30 squared divided by the product of D60 and D10, where D60 and D10 were previously defined, and D30 represents the largest particle size you can read off to your log chart that is smaller than 30% of the sample material. Confused? Don't worry, we'll work on an example together. Once you computed your coefficients, you can then make reference to a unified soil classification system like the one shown here, which will help you classify the soil sample you tested according to standard accepted guidelines. The table in question is actually found also in your textbook in Figures 2 and 3, pages 20 to 22. In fact, you can compare your results against the provincial standards for the province of Ontario, which I linked for you online under your Assignment 1 folder in Blackboard. The next part of this lecture will be a quick example about how to identify a soil sample after it has been passed through a sieve analysis.